Okay, so please, everyone, welcome to the next GOAT seminar. Today we have our own Maria Saumell talking about guarding 1.5 dimensional terrain with imprecise viewpoints.
Thank you, Michal. This is John Ward with Vahideh Keikha, who used to be my postdoc and still works at the Academy of Sciences. Maarten Löffler, a colleague from Utrecht, and Pavel Valtr, who works at Matfis. Before I forget, the slides are adapted from Vahideh's slides. And this paper won the Best Paper Award at IVOCA, which is great for a PR, but personally I think that this says very little either about IVOCA or the PC or something. But okay, it won Best Paper Award at IVOCA. So, yeah, that's it. Here, this is the outline of the talk. And so this is the problem statement. This is the object we will be working on, 1.5D terrains. These are defined as X-monotone polygonal chains. So we call it 1.5D because the object lives in 2D, but in a way, since it's forced to be X-monotone, somehow. Well, that's the terminology we use. And then we deal with problems related to visibility. So we need to understand what it means that 2 points on the terrain are visible from each other. And the definition would be the same one as if we were standing on the terrain. So if I'm standing at M and somebody is standing at B, I would see them, right? So M sees B. But on the other hand, standing from M, it would not be possible to see Q or W because the terrain is blocking. Okay, so the terrain is defined as the X polygonal chain, but you have to imagine that below there is like proper terrain that is blocking visibility. Okay, so this is the intuition, and the mathematical definition says that 2 points see each other even only if the segment that connects them lies entirely above or on the terrain. It cannot go under. So M doesn't see W because you see this segment that connects them at some point goes under the terrain. And this is it. So this is important, otherwise we don't know what we are talking about. And this is the problem, I jump straight, that we work on. So our input is going to be such a terrain with n vertices and a subset of some of the edges. We choose m edges of the terrain. And now what we want to do is select for every edge 1 point, one particular one, such that together, when I see all the parts of the terrain that together this m selected point see, it has to be as big as possible. Okay, so I want to see as much of the terrain as possible with the restriction that I have to choose 1 point for each of these edges that are given in the input. Okay, and since terrains are defined as the chains, so when I'm speaking about portions, how to measure a portion is just the length, okay, of that part of the terrain. Okay, so this is the problem we are studying because it was not studied before. So let's see a concrete example with m equals 1. So they give me this terrain and this particular edge, and they ask, choose 1 point of this edge that sees as much as possible of the terrain. So any guesses? Who is the solution?
In the middle.
In the middle, very good. And what is nice about this example, so the solution is indeed in the middle, but what is kind of, important is that it's not an endpoint, okay? Because if I stand at this endpoint, I see this part. If I stand at the other, symmetric, but if I stand in the middle on top of this, I see this extra part. So this tells us that the problem is not totally trivial, because if the solution was always one of the endpoints, there is not much to study. Okay, so here is an example with one imprecise viewpoint. And now why am I talking about imprecise? Because we can see this problem under the framework of imprecision. Okay, imprecision is kind of a new model in computational geometry. I think this is maybe my third talk in this seminar speaking about the problem on imprecision. And the idea is, so traditionally in computational geometry, we work with problems where the input is a concrete set of points or a concrete set of segments and so on. But in imprecision, actually, the input is a set of regions. That can be, for example, a disk, because what is the idea? That I don't know where my points are. So they give me a region, and I know that the point is somewhere in the region, but I don't know where exactly. That's why the input is a region, and it can be line segments, it can be disks. And then, well, there is infinite ways of choosing a point for each region. And every time I choose one point for each region, I call it realization. And then I go from a set of regions to a concrete set of points. Okay, here we have a realization if the regions are just segments. I choose one point in each segment and it becomes a realization. Here you have a traditional input in a computational geometry problem, just it's already the input is a set of points. But then since I have that freedom, because I have infinite realization, these optimization problems come into play. Like for example, I can choose pretty much any problem and study kind of the extreme variance, yeah? How to choose these 3 points so that convex hull is as big as possible or as small as possible, and so on. I can restudy everything under this paradigm, and this is what we do here. Yes, because our region are these edges of the terrain, and I want to choose 1 point for every edge. So our problem falls into this setting. And let's see the main results. Well, it turns out, unfortunately, we don't know how to solve the problem for general M because it doesn't seem to have much structure. So at least what we can do is present an approximation algorithm that returns quite efficiently in n plus m log m a 1/2 approximation. Then we can solve the small cases meaning m equals 1 or 2 imprecise viewpoints. And then we can solve a related problem that, okay, maybe I will go into this later. Now it's not so important. So let's start. First thing, approximation algorithm. The approximation algorithm is based on a very simple observation that tells us that if I consider some point on an edge, no matter where, what this point sees is I can see is a subset of what the two endpoints see, or I can see that anything visible by this guy is visible by at least one of the two endpoints. So for example, this portion here is visible by the left endpoint, but not by the right, that is not important, and so on. Okay, so basically, the two endpoints together see the same or more. And this is very easy to prove and is the base for the approximation. Okay, before I explain the approximation, one more definition, which is simply the definition of view shape. Yeah, all the time we have a point, and we are trying to compute all the portions of the terrain that it can see. So this is what we call view shape. Okay, the union of the portions that are visible, and then when instead of having one, I have many of these viewpoints, we denote it like this: V's of TP, which is simply the union of all the view shapes of all the viewpoints that are in P. Okay, so we need these definitions. And now, what is our approximation? We are going to define two realizations, two concrete ones, and prove that the best of them gives you the approximation. So which is the first realization? We have this bold edges that are the input ones where we can play an imprecise viewpoint. In P1, we put 1 point. So we choose for every of these bold ones, one of the endpoints. And I put it in P1. This gives me a concrete realization. Now what do I do in P2? I choose the one that I didn't choose before. In the left one, I put in P1 left endpoint. So now I put in P2 right endpoint. Okay, so together, they contain all the endpoints of the input edges. Okay, so these are the two realizations. Now it's easy to see that the rest of them gives the approximation, and this will be the only proof in the talk. Some people claim that every talk must contain one proof. So here it goes. So let's take P star as an optimal realization. That would be the solution of our problem that we don't know how to compute. Now, what P star sees is the union of what each of the particular points in P star sees. This is the first part. But this, as we saw in the previous lemma, for each of them Pi star, the selected points, what this guy sees is included into what the two endpoints of that edge where Pi star is see. So I can express it like this. So EIL is the left endpoint of the edge EI, where Pi star is, and EIR is the right endpoint. Okay, but now this, since we put every endpoint ended up in one of the two realizations, this part here is actually exactly the union of what P1 and P2 see. So, perfect. What the solution sees is a subset of what these two realizations see. So, okay, now I just put these bars to denote the length, because what we are maximizing is the length, right, of the visible portion. So then this is smaller or equal than this, which can be expressed, which is smaller or equal than the sum, and the sum is smaller or equal than 2 times the maximum, which tells us that the maximum is bigger or equal than 1/2 the optimal. Oh, okay. Not a great factor, but at the same time, very, very simple. If anyone has an idea on how to improve the approximation factor, we would be happy. So, okay, this is the lemma. Now the algorithm is obvious, right? We are going to select this P1 and P2. We are going to compute the portion of the terrain that they see. This we can do it efficiently by a previous result of some of us in n plus m log n. And then once I compute what each of them see, now I just pick the best and that's it. Okay, so this is the first result. This one have approximation algorithm. And now, as I said, the next results are the small cases. The first small case is what happens when I only have one edge. Yeah, I only have one edge, and I have to choose which point in the edge is the one that sees the most of the terrain. Now, a problem is that this problem doesn't seem to have like a structure. Like we are not able to find a combinatorial characterization of the candidates. We, very often in this type, in computational geometry problems, you say, oh, the candidates for the solution have this shape, so I just traverse them, but we cannot for these problems. So what we do is very, natural, what you would do when nothing else comes to mind, which is pretty much parameterize the problem and look at the functions. Now let's go step by step. I have this edge E, where I want to find the solution to my problem. So I'm going to parameterize it by 0, 1. So every point in the edge will be some value between 0 and 1. And then now we are going to study which portion each of these points here, which portion of, I fixed a second edge, which portion of the second edge is. So I fix the second edge, which for now it will be to the right. And then what am I interested is this function that pretty much tells me how long is the portion of EX that this sigma sees. So in this case, this is quite boring because it sees everything. But for example, if I put some obstacle here, so it sees this edge, and this function gives me this length, how much of the edge I see. So this is the function that for every edge of the terrain tells me for every value of sigma, how much of the terrain I see. Because we want to see as much as possible. And then our goal is to understand how these functions are behaving, if they are simple to manage or more annoying. Here is another example. Okay, so we want to describe. Now, to make it more interesting, is there anything that you already see for this case about this function? If I assume that EX is to the right, it will be monotone. It will be non-increasing. Exactly, monotone. Exactly. So this is the second part, that it's non-increasing. And then it's also piecewise defined. Okay, I want to make figures. I did not manage, so let's see if I can manage now. So why is it? So what can happen here? For example, let's say at the beginning I have some points that say absolutely everything. So my function starts here. I see the whole length of this edge. Then what can happen that at some point I have something that obstructs me. So as I move sigma here, I start seeing less and less. I have some function here. Then even what obstructs me can change. So at some point it can appear a second guy. And now I'm still seeing less and less, but this function is changing until eventually maybe I arrive at 0 or I reach the end of the edge or something. So it's a piecewise defined function. And this is important. Okay, and it's non-increasing, except you see at 1. Because at 1 the behavior can be strange. Because if this is my edge E and this is my EX, and the terrain is, for example, going like this, I see nothing, and when I reach the final point of the edge, and all of a sudden, I see the whole EX. So at 1, it behaves weird, but before 1, it's fine, it's monotone. Okay, so we know a little bit about it, but we need still more. And the lemma is this, that basically, so it's a piecewise defined function, and each of the sub-functions can either be a constant, this is the first case, between 0 and the whole length, of course, or it can have this this more annoying shape, which I think is a hyperbola, right? Hyperbolic function. So it can have one of these two shapes. Of course, the first one is much more treatable than the second, and also important, in how many pieces does it get cut? Linear, at mod linear. It doesn't blow up so much. Okay, when do we have the second case? In this case, where we have a vertex that is obstructing the visibility like this. So when we are around at some point like this, and this is telling me which portion I see, the function giving me this length that I see has this hyperbolic function, this hyperbolic shape. So it appears there. Okay, so now we understand how this function is behaving. So what is our problem? Well, we want to maximize, so we did the work for one of the edges. Now I want to for one of these edges, right? But I'm not interested only in seeing this edge, I'm interested in seeing the whole terrain. So I have to sum all of these edges, which tell me for every edge how much I see. And now I have to maximize, right, to be able to see as much as possible. So our problem, we can rephrase it just simply as solve this, maximize this function of the sum of all the lengths. And we need, okay, so how efficiently can we do it, right? We not want to spend so much time for the case m equals 1. Well, the nice thing is that the number of pieces at overall edges is also linear. So I said before that when I just fix one edge and I construct the function, it's going to be linear number of pieces. Actually, so this would tell me that maybe if I repeat this for all EX, I have quadratic in total, which would be quite bad. But actually, we have a theorem telling us that this is linear. So over all possible EX, when I see how many pieces each of these function gets, is also linear, which makes it more treatable. So once we know that this is linear, always a kind of reasonable goal is to compute it in n log n, right? And this we can do. So we can compute all of these functions in n log n, even using, well, you can do it for Scratch because none of this is too difficult, or one can use previous results from previous people. So perfect. We can compute the functions in n log n, but we still need to optimize, right? And now what could happen here, I don't want to show it yet, is how to optimize it, like how many, we are interested in maximum, so how many local maximums I can have there. Because, so pretty much I have this thing here. Here is my 0, 1. And for each ex, I have a function that, for example, starts like this, then it changes, then it changes, then it goes to 0. So every time that the algebraic expression changes, I can make a mark like this, and this I can do with all the functions. For example, I can have one that is increasing, so it starts constant, that it increases, then it again increases, and so on. Okay, so I can take all of these points and kind of project it, right? Because I always have to work in one of these sub-intervals, right? Because in one of these sub-intervals, the algebraic expression of all of the functions is the same. And then I can work with the sum. So we prove that there is linear number of these sub-intervals because the total number of pieces is linear. So, okay, what happens when I look at one of these sub-intervals? Well, when I look at one of these sub-intervals, I have some functions that are decreasing, which corresponds to the edges that are to my right. Yes, as I move sigma, I see less and less. But I also have some functions that are increasing, because to my left, going in this direction, I see more and more. So we could be very unlucky, and even in one of these sub-intervals, have many local maximum. Because in general, n increasing functions plus n decreasing functions could have n or whatever local maximums, which would be quite bad. But we can prove that this cannot happen. Like, even though in one of these sub-intervals I have a sum of some decreasing and some increasing, we can prove that the sum is either constant or cyclic concave, which tells us what? About the local maximums.
It's like
That,
one of the points that will change.
sorry?
It will be one of the points where the functions change.
Well, or I can have also a local maximum here, right? But I can, like, I have at most one. So when a function is strictly convex, I have at most one local maximum. So the solution is either at this local maximum or at the point where it changes, because yeah. So that's perfect, because in each subdomain I have at most one local maximum that I need to check together with the others. Great. So here comes the magic. In the real RAM, if I have this, if I take one of these sub-intervals, and I get a function with a degree n potentially, and how do I find the local maximum? I can do derivative and make it equal to 0. So we can do it in constant time. And then obtain this result, that we can solve the problem in quadratic time. Yes, because we have, again, n of these sub-intervals. In each sub-interval, I have a function that potentially is a fraction like this, but I know it only has one local maximum, so I make the derivative equal to 0. I see if I get something within the range, and that's it. Then I also check these two guys. And in the real RAM, I can do it in n square. More realistically, I guess one would use numerical methods, because, yeah. Okay. Okay, so this is our first theorem. And now, well, we just observe that with this result, we can solve this other problem, which tells us, given a terrain, find the point that sees the maximum of the terrain. Find the point on the terrain itself that sees the maximum. And this is because we know how to solve for one edge, right? If I give you one edge, you know how to find the best within this one edge. So just run our algorithm for every edge, and you will find the global maximum in n square. Now, what is interesting is that never looked at this problem before. So there are many problems on visibility in 1.5D terrains, but nobody look at this, find the point that sees the most. So it's another contribution that we do. Actually, it is not true that nobody did it. Somebody did. Yeah, somebody claimed the result, and they claim it even in a general, because they're saying if I have a terrain and then somebody gives me some value of h, find the point at this altitude of h with respect to the terrain, which means that if I am using, find the point at an altitude of h that is the most. So somebody claimed to have solved this problem. Notice that if we put h equals 0, we have our problem, because in our problem, the points must be on the terrain. In their problem, it's more general. They allow them to be up. The value of h is fixed. So somebody claimed that this could be solved in quadratic, but it was not true. So we correct some I don't know, mistake in the literature. Yeah, and what happened is that they did a characterization that was wrong. Okay, this was published in some bogus conference coming from some master thesis, I don't know. But you can find a paper with some strange conference. So yeah, basically they characterize a set of candidates. So they say the solution must be in one of these places, and their characterization is wrong. Because really, this problem is like, it doesn't look like anything nice is happening. And okay, this is our counterexample that for this particular terrain, the solution is not in any of their candidates. So they were, if you are interested in what were their candidates, they were saying that the solution is either at the projection of a vertex, so a point like this, that when you project, you are at a vertex, or then something like leave the terrain by h, prolong the edges like this, I get these intersection points, project, and these are the other candidates. But this is, well, this point here, which is the solution, is not the projection of a vertex, and it's not it doesn't come from this. So, okay. So we are the first one to solve it correctly until the next ones comes and claim the contrary. Okay, how much time? M equals 2, or maybe a bit of time. So what about M equals 2? This, as you can see, we are taking very straightforward approaches. Look at the functions, giving the length, and maximize them. Can we do the same for M equals 2? Yes, we can, because this is still quite manageable. So now I have two edges where I have to place a point, EJ and AI, so I can again parameterize. Points here will be parameterized by sigma, points here by delta. Both of them run from 0 to 1, so this is my space now. Here is sigma, here is delta, this is 0, 1, 0, 1, and every solution, every realization is 1 point here. Okay, so this is clear. And then I can again try to, like before, our space was just the 0, 1, right? And I was dividing into subintervals, such that at every subintervals, all the functions were defined by the same algebraic expression, and I can work with the sum. So now I can do the same separately. I can separate one part of the domain like this, and I can do the same for the other imprecise edge, and now I get a grid, right? Now I get a grid like this, such that for a portion of the grid, all the functions associated to one or the other have the same algebraic expression, so I can work with them. Now,
But there can be also parts that can be seen by both.
Interactions, exactly. So now the step that is missing is to deal with the interactions, because okay, the function is the same, but if there are parts that are seen by both, I cannot sum them, right? I cannot say that here what they see is the sum of the one plus the other, because maybe they are seeing the same, I cannot sum it. So this is the next step, that now I need to even subdivide one of these to take this into account. I'll say how, so I need further subdivisions to be careful with the interactions. And when I have the final subdivision, now I have an arrangement and I can go phase by phase and optimize, because I know exactly what is happening there. So now to finish, what are the possible interactions? For example, first figure. So the two guys. So I'm only considering the sub-interval sigma 0, sigma 1, delta 0, delta 1. So in both cases, actually, they always see the same. What am I doing? Yeah, okay, here is sigma 0, sigma 1. Then here is delta 1, delta 0. So for example, in that case, for all values in sigma 0, sigma 1, I see exactly the same portion. And for all values in delta 1, delta 0, I also see the same portion, but I cannot add them because they are overlapping. But in any case, for any value here, what do I see? The whole edge, right? Because no, I see the whole edge, right? Because one of them says this, and the other says that. So together they see everything. So I really don't need to subdivide. I just need to make a note that here they see the whole edge. Perfect. But I cannot sum. If I sum, it is wrong. Okay, so another case. I only do the first two, and I think that's enough. Okay, what is happening there? Delta 0, delta 1, all values there, they see exactly the same part, which is this part here. But for delta 0, delta 1, I start seeing more, and at some point I see less, right? I start here at delta 0, so I see more, and then I see less. So how do I do this? This value, where they see exactly the same, if I call it delta prime, for example, I have some value here, delta prime. Yes, I have a horizontal line. Now, below delta prime, delta c is more, right? Because I'm here, delta c is more. So below delta prime, take function for delta, because it is more. Here they see the same, but after delta prime, actually, the sigma c is more. So after delta prime, take function for sigma because it is more. So, okay, my domain gets subdivided by a line, horizontal line, telling me below the line, choose this function, above the line, choose that function. Sorry, I went out of. So, okay, and then, well, there will be cases, well, it will be computationally more difficult because I will get a curve that it will not be as nice as an horizontal or vertical line. I will get a curve like this that will tell me below the curve, take the sum, above the curve, take one of them. You see, but I can do it. I can just look at the cases and do it. Okay, so then I get the complete characterization. I have for each portion exactly for every other edge how much they see, and I can optimize again. And actually, in the conference version, we just said we can do it in polynomial time, and I think it's into the 5. We are finishing now the journal version. Okay, so open problems. Obvious ones. Can we continue this for constant values that are greater than m? Because from theoretical point of view, it looks like yes, just the domain is getting more and more, well, the dimensions of the domain is increasing, but it looks like with a lot of patience, one can just look at all the cases and subdivide the domain, blah, blah, blah. Maybe there is even a result that one can use as a black box and that can solve this. But this is the first one. I don't know, is there any result like this that we can use without having to, I don't know, explain things in all the detail? And number 2, of course, what happens for general values of m is a problem hard. Yeah, these visibility problems have some structure, but we don't know how to solve it. Like some structure is there, some domination. Sometimes you are sure that this guy sees more than the other, but somehow not enough for us to develop an algorithm. So is it tractable or not? So thank you very much for your attention.
Is it clear that for general values of m it's in NP, or is that part of the open problem? Is it clear that it's in NP?
Good question.
Maybe thought of a question. Yeah. Okay.
So I guess no.
Other questions?
It's in text.
Some more questions? Okay, if not, then let's thank the speaker.